So today we're going to try to go through all the different design patterns, and then next week we'll give you guys an assignment. After this class, you're going to get an assignment on design patterns, and then you'll get a couple classes to work on it. In class will be like a final programming project assignment. They'll be using a lot of design patterns. Okay? So the last time we were talking about design patterns, we basically had this example with a pizza, right? Just to refresh your memory really quickly, because it's a pretty straightforward example, we had a pizza, which was a product, and the product was pure virtual, right? And so then we made three different kinds of specific concrete pizzas, and then we created a pizza factory. So basically, you told the pizza factory, so we could create a pizza as long as I could send in a pizza type, which was an enum. And so what the pizza factory would do is say, okay, based upon what you want, if you want this, I will construct one of these concrete subclasses, or this one, otherwise I'll throw some kind of exception. So that was the basic idea. And then we had some methods here to give you some values. And then basically to test the design pattern, all we did was we called the pizza information method, which sent in the pizza factory enum of one type, another type, a third type, and what the method would do, the pizza information, basically it would actually call the pizza type, and then give you the stuff about it. So that was a design pattern, which was a factory design pattern. Okay, so now we want to talk about the abstract factory pattern. And the difference here is that the factory itself, whereas here in the pizza factory, notice that this class was a concrete class. It was actually building objects, constructing objects. So in our abstract factory examples that we're going to look at, the factory itself will be an abstraction. And I have two examples, and I'm going to look at the second example, and then you can look at the first example by yourself. The first example I found to be kind of boring, so I decided to add another example, which I did. Okay, so basically, this is the first example. So nice thing about it, we're going to skip the whole thing. Okay, but it's a nice example, and so now we're going to go to another example, and we're going to go back to cars. So we're going to be building cars in an abstract factory design pattern. So first thing we're going to do is, before we get to the factory, let's create some tires. Now if you look at this class, there's a tire class, and then we're subclassing it for a simple tire and a luxury tire. All right. So is the tire class abstract? The answer is?
Yes.
It is not abstract because it doesn't have any pure virtual methods. So in fact, it doesn't have any virtual methods even. So it's just a simple class that says, okay, tire has a name, and it's going to have some kind of pressure, tire pressure. Okay? And then they give you a constructor, and the constructor says, okay, here's the name of the tire, here's the pressure, and there's a member initializer, and then there's some get methods. So the tire class actually is a concrete class, but then we subclass it, and all we do in the subclass is create a simple tire, where the simple tire constructor calls the tire constructor, giving it the value of simple tire and the pressure at 75. And then the luxury tire also subclasses tire, and it calls the tire constructor, giving it a different name and a different pressure. Straightforward. So nothing abstract here. It's just going to be part of the car. So the car is going to need to have a tire, so we're going to do it this way. Then each car is going to have a body. So again, we're going to do the same thing. The body, and again, very simple classes. The body is going to have a name. It's going to have a strength. Okay? We could have a weight or whatever we want to do. And so simply put, we're going to have a constructor. Again, member initializers for the two properties. And then we have a couple get methods. And then we subclass it into the standard body, which is going to be called simple body at a strength of 75. And then a luxury body with a different name and a higher strength. So again, two pieces that we're going to make up for the car. One is going to be a tire for one kind, another kind. and then a body for one kind and another kind. So far, so good. Now we're going to create the car class. The car, is that an abstract class? Okay, so the car, is it an abstract class or no? No, it's just a regular class, concrete class if you will. And so the car basically is made up of, has a name, it's going to have a tire, or a set of tires, whatever, and it's going to have a body. And so the car constructor basically, you're going to give the name of the car, which is going to load it into the name, and then it's going to set the tire to the tire, and set the body to the body, and then it's going to print the details. So the car will be constructed in a factory, but the factory will be an abstract factory. And the reason for that is because one car factory will construct only ordinary cars or regular standard cars, the other one will construct luxury cars. So therefore, if those two factories are going to do the same kind of thing, then we're going to need an abstraction, which is going to be the abstract car factory, which is going to be implemented by the actual factories. So the car is a specific product, and it will be made. So again, you can see that this car can be constructed by having, you can stick in a luxury tire or ordinary tire, same thing here, regular body or a luxury body, okay? And so now we're going to go to the car factory. So the car factory, here is our very first abstract class, and it's an abstract factory class. So build tire, and then build body, and then we're going to have another pure virtual method called build the whole car. So we're going to build the tire, build the body, build the whole car, but we're not going to do any of the work in the abstract factory class. We're going to subclass that out to the specific factories. So the two factories we're going to have is we're going to have a simple factory, and we're going to have a luxury car factory. So let's look at the simple car factory. It is a subclass of public, and of course we have to override 1, 2, 3 pure virtual methods. So to build a tire, which returns a tire pointer, we're simply going to return a new simple tire because we're building simple cars. And to build a body, we're going to simply return a new simple body because we're building simple cars. And so therefore, when we build the whole car, we're going to return the pointer to a car, okay, by creating a new simple car. So we give the name of the car to the car constructor, and then we're going to set the tire to the build tire, which means we're going to create the simple tire, and we're going to set that equal to it. So we're going to set the tire of the car to the tire that we're going to produce. We're going to set the body of the car to the body we're going to produce, and then we're going to return the car because that's what we do. We're going to return the car. Okay, so build whole car is going to give us that. And the luxury factory, again, is going to take this abstract factory. We could call this abstract car factory or just car factory. Certainly abstract wouldn't be a bad name. And so the luxury car factory also subclasses car factory and overrides in its own way. So building a tire returns a new luxury tire instead of simple, luxury body instead of simple. And when you build the whole car, it puts the label of luxury car into the car, and then it simply sets the tire of the car to the build tire, and the build tire is going to take care of, make sure it's a luxury tire in both cases. And that's it. So now, the advantage of this is you're going to see if we're running a program, so it's a test program. So in this case, we have a main driver, and so we have pound if def simple car. Notice that we pound define simple car for the preprocessor, and then therefore this condition will be true. So therefore this code will be passed to the compiler. Okay. Elif luxury car, that's going to be false. So that's not going to get passed to the compiler. So therefore this gets passed to the compiler. Car factory, pointer factory equals new simple car factory. So we create a new simple car factory, and we assign this pointer to the factory pointer. So that, remember, factory is a pointer to car factory, which is an abstract class. And we assign it a pointer to a simple car factory, which extends car factory in a concrete fashion. And so once I have a factory object, I can then basically say, okay, factory, which is a pointer, I'm going to invoke the build whole car method. So so the abstract factory will build the car using its actual value, which is the simple car factory. Okay, and then once I do that, I get a car pointer, then I can go to the car pointer and I can print the details of the car, and you can see as I run the program, I get this information. The car name is simple car, the tire is simple tire with a pressure of 75, the strength is 75, simple body. Now, what I did was, I ran the program again. This time I commented out simple car, and I uncommented pound-defined luxury car. So when I rebuilt my project and I reran it, then pound if that simple car was false. Therefore, this code was not passed to the compiler. The elif code was then passed. Luxury car was defined. By the way, I didn't have to even say elif luxury car. I could have just said pound elif, and it still would have been the case. Although I did define luxury car when I uncommented it, and then undefined that one when I commented it. But at any rate, so at that point, factory, which is my abstract pointer to that abstract class, gets set to a luxury car factory, which is a different implementation of the abstract class, but it's the same thing. So factory, car factory, pointer, factory, car factory, pointer in one instant. So again, I did it with using a preprocessor just to split them based on the pound if def. Once I did that, then the output of the car, basically you can see that the same code, the same factory, right? The same factory, although different instance of the factory, produced a car that was different. Abstract factory. All right? Questions? So I urge you to go through my examples and to try to run these examples. If you get the project and you try to do your own without having to testing these things out and messing. No, you could create a different car factory now. You can have a sports car factory. Okay? And of course, that way the driver stays exactly the same, because I still create just a regular factory. But all I need to do is to construct a sports car factory, and I set it equal to my factory pointer, and as long as I subclass the abstract factory, it works just the same way. So that's the advantage there. Okay, any questions about that? All right, not too bad. So these, all of those patterns that we're looking at are what kind of patterns again? Creational. Yep. So, and let's review what they are. What kind of patterns did we come up with? Singleton? Not simpleton. Singleton, okay. And what's the next one?
Proc. No.
What else? Proxy? What else? Prototype? What else? Builder? Factory, and then abstract factory. Okay. So we are doing outstanding work. All right, let's go to part 2. Is that part 2? Did I say
Part
2?
3.
That says 3?
Yeah.
What does this say?
1.
That's part 1. We don't want part 1. How about this one?
Yes, 2.
That's 2. That's what we want. Alrighty. So, do you remember what type of patterns we're going to look at next? Do you remember what the next set was?
Above 1. No, that's 3.
Yeah, structural.
Structural. And what exactly does that mean? No, that's not the one I want. I chose the wrong one.
3. Yeah.
That's going to be the last one. Okay, I cannot see
The
this.
above one,
Okay.
yep.
Is this
Yep.
2?
Yes.
Okay, I think so. I'm telling you, man, it's not easy. But my glasses, I can't see anything. All right. I pretend I can see something, but I really can't. Talk to your parents; they'll tell you what I'm talking about. Try one more time. Here we go. All right, so we should be good on that one. Okay. completely different color. Very strange. Okay. It's not getting the colors I want to get. Okay, so we are going to look at structural patterns. And structural patterns are, so creational patterns are basically the way we design our program to create things, to build things, to use factories, to prototype, right? To proxy, and create other types of patterns. Okay, structural patterns are basically the way classes are going to be organized. So this is a static view of the classes. So one of them is called an adapter pattern. How many of you have gone to different countries? Most of you have gone to different countries, right? And if you notice in different countries, when we try to plug in an American plug, it's not going to work. What's going on? So years ago, many years ago, before you were born, it was impossible to bring any appliances or devices to a country that had a different plug or possibly different voltage. In fact, if you wanted to do it, you'd have to bring these very heavy devices. They call those devices?
Converters.
Yeah, they call them adapters. And they were very heavy duty because they had to convert voltage, they had to change the format of the plugs, and sometimes they worked. And sometimes they blew out your appliance. So it depends on how lucky you were. So it was not easy. So adapter basically is sort of the software equivalent where we try to make two unrelated interfaces work together. You have one interface that has 3 holes in it, and you have another one that has 2 prongs in it, and it's not working. So what we have to do is we have to put something between them to adapt those two things so they can work together. Because they basically could work together if they could only plug into each other. So that's what we're going to try to do, make them adaptable. Okay, so the classes do not have compatible interfaces. So it enables the use of several existing subclasses. I have this piece, it works great. I have this piece, it works great. They just don't work great together. So I want to make that adapter work. So the idea is we have 4 classes that we have to implement. One of them is going to be the target, the adapter, the adaptee, and of course the client is going to drive everything together. So you can see basically the target is here. Now, adapter, what is this using UML? All of these are classes or interfaces, right? So what is the target? It's a class. What does this symbol mean?
Inheritance.
That's inheritance. So basically the adapter is a subclass of target. Okay? The client wants to access the target. And what we're doing is we're having the adapter subclass of target. But then we have another class here, and we have a different kind of symbol here. Anybody know what that means? What does this UML symbol mean? It's different because it basically doesn't, it looks different, right? It doesn't have this thing right here. And also, this is the same as this one. Anybody? Huh?
It's an access symbol.
It's an access symbol, or sometimes known as the dependency symbol. Dependency symbol. It means that the client depends on the target, and the adapter depends on the adaptee, and the adapter subclasses, or is a subclass of target. So let's see how that's going to be put together. So in our example, what we're going to have is we want to use something called a circle. So a circle is going to be some class that exists. Somebody made a beautiful circle class. And the adaptee is going to be a standard circle. Okay? And the circle adapter is going to be the class that's going to be implementing the pattern. So let's take a look at how this is going to look. So the standard circle is the adaptee. It's a useful class, but the interface may not be what we are expecting. So the standard circle exists. It's going to be this one. It's a standard circle. So the adapter is going to depend on the standard circle. It means the adapter is not going to create the methods of the standard circle. It's going to adjust them for interfaces for the clients. So adapter will depend on the implementation of the adaptee, but it will adapt them for a different access. Okay, so the standard circle, basically, you can see that we are creating the standard circle with a double radius, which we can certainly do. And so the constructor says when we add the radius in, then we're going to assign it into our local radius called radius underscore here, okay, which is fine, or we can just say this pointer radius and just get rid of the underscore. And then we're going to say cout standard circle, create radius is equal to such and such. And then when we're going to draw the circle, we're going to say, okay, this is standard circle, and we're in the old draw method, and here's the radius. So that's a basic way, and of course we could actually do some drawing if we wanted to, but we're going to try to keep it simple. So that's a standard circle. Now we're going to look at the interface that we want. Create an abstract class target which has the draw method we need. So we want to, the client wants to say draw. It doesn't want to say draw old, it wants to say draw. So we need to have a class, and the class will be called circle. And the class will have a virtual draw method, which will be pure virtual, and that's the class that the client is going to access. So now, in order to implement this adapter, we have to subclass the target using an adapter. So this is going to be our circle. The adapter is going to actually implement the draw method, but it will actually use the old draw because it wants to use all the functionality of this already well-established class, and it wants to make the client use this new interface. Okay, so what we're going to do is we're going to create circle adapter. That's our big design pattern. And you can say basically that it's going to, the circle adapter will subclass circle, okay, in a public way. But in our sneaky C++ way, we're going to also subclass standard circle in a private inheritance. So what we're doing is we're creating this, we're actually making the circle real, the circle adapter real, which means we're going to have to create this, abstract draw method. We're going to have to implement draw. Here it is. But we are inheriting privately from standard circle because we want to be able to utilize what? The actual method that draws, which is called, what's the method called? Okay. Let's go back. The method is called old draw, but we want to use the draw method. So what we're going to do is we're going to subclass circle so that we can override the method called draw, and we'll subclass standard circle because we want to do what? Because we want to utilize the code for old draw, which could be complicated and legacy code, something that we're going to interface into. Okay, something existing, tested, works well, but this new application needs a different interface. That's what we're doing. So, the circle adapter basically says that if you want to create a circle adapter, then you're going to give me a diameter, but then the standard circle needs, let's say, a radius. So what I'll do is if you want to construct a circle adapter, I will construct a standard circle, and I'll compute the radius for you by cutting the diameter in half. And I'm going to say cout circle adapter, create diameter equals, and I'm going to give you the diameter name. And then if you want to draw the circle, then I'm going to say, okay, circle adapter is going to drawing, and then all I'm going to do is I'm going to call the old draw method, even though you're calling the draw method. So the client is going to use the draw method, and I will call the draw method. Now, can the client call the old draw method directly? No, because why? Because we did a private subclassing of standard circle, so old draw is hidden from the client, but we can still access it. Because remember, the private inheritance allows us. Yeah, a question or? Yeah.
So how is this pattern different from a proxy or wrapper?
How is it different from a proxy? Well, I guess the only way it's,
I think one big usage of this pattern is if you want to add like more functionality to the current class. For example, if we need to add another circle with another behavior, but we need to make the same call. One usage of this one.
so, yeah, so that's one. So there is a similarity to them. The proxy pattern, one of the proxy patterns that we looked at is basically if we access the outer object, we get the inner. We can get inner. So the proxy, in a sense, is an ability. It's I think part of the big reason is that this one simply allows us to call draw every single time. So it's not constricting or controlling how we call it. It simply adapts the draw call to the old draw call. That's, I guess, the biggest difference. There's no proxy logic here. The logic is simply an adaptation of one to the other. That's, I guess, my best answer here. So there is a similarity. So you're very good to catch that similarity. So now, if we're going to test this adapter class, we can say circle pointer C equals new circle adapter, 100, okay? And that 100 is what? It's a diameter. What's going to happen is that the circle adapter is going to construct what? What's the circle adapter going to do? It's going to construct a standard circle with a radius, which is half the diameter, right? And then, but to me, the circle adapter is the only thing that I'm aware of as a client. So then I'm going to, okay, circle draw. So it's going to draw the circle with a radius of 50, even though I constructed. So even though there's no draw method in a circle adapter, but the circle adapter will simply have the draw method called the old draw, and the old draw will draw a circle with a radius of 50. So I'll get the behavior of the legacy code, which is, and the legacy code is simply the standard circle. So that's legacy code. And typically adapters are used when we're trying to use something that pre-exists as a different interface than our new system is using. And that adapter could be quite complicated. You could have an adapter that goes, for example, from Java to C++. You could create an adapter like that. Then it's going to be a little bit more complicated to do it, but it can be done, and it is done. So you could actually have Java call C++ legacy code. So therefore the adapter would really would be a language adapter. I used to do a lot of that kind of stuff in C++ in the Java class. Not so much anymore. I think I throw it back next semester. Next semester we'll invoke DLLs in Java. I think that'll be good. It's useful. It's useful because you can have some very specific fast codes. Okay, so that's the adapter pattern. All right, structural pattern. So we structure, and the reason you can see it's a structure, well, here's the structure. So here's the client. The client is basically using the target, and the target is just, in a sense, an interface or an abstraction, which is implemented here, which is depending on here. So adapter basically is subclassing this and depending on this one, and the way we did the dependency is there's a couple ways to implement dependencies. One of them, in our case, is basically we're still subclassing here. But we're subclassing private, which means that we are not, adapter is not an adaptee. The adapter is implemented as a adaptee. So there's an as a inheritance here, and there's a subclassing of an abstraction here. And so the client is going to depend on this one, but actually this one is going to be implementing the old legacy code. So the legacy code is the adaptee. Okay, any questions on that? Anything else? All right, so that's one pattern. Let's look at the facade pattern. We talked about facade. Anybody speak French here? Nobody speak any French? Oh, you speak French? You actually speak French, right? Okay, because you're from Haiti, right? So of course you speak French. So, qu'est-ce que c'est la façade? What does it mean?
Can be the wall or something
Okay, something that hides maybe something that's in the background, right? So something, a facade. Like when somebody acts one way, like they're acting really nice, but you know they're really not a nice person. But why are they acting? They're putting on a facade. They're acting in a certain way. But sometimes a facade, we can say, for example, let's say you have an ugly building, and people don't like to go to your store because it's very, very ugly. So you make a nice, fancy front. We sometimes call that in English a facade. So, oh, it's so beautiful, but you go inside, it's still ugly. But people are still going to go in because they like it looks very nice on the outside, so they think it's going to be nice. Maybe it's nice on the inside. Maybe it's okay, but the outside is very ugly, so we'll put a facade, which means we don't change the building, we just kind of make a new front that looks nice. Also, a facade, we can think of a facade as a front end or a distribution center where everybody goes into some center area. So you can think of sort of the receptionist in a building is sort of the facade into the rest of the building. Because you do not go to talk to the director until the receptionist says, okay, you can go talk to the director. You go in, you have to register with the director, with the what I say? The receptionist. And the receptionist says, do you have an appointment? No, I don't have an appointment. Well, if you get an appointment, you have to wait 2 hours availability. So the receptionist basically is acting as a facade for many different systems. So you have to go through here to get to different places. So it's kind of like a distribution to different other components. Okay, so one example you can have is you can have basically a customer service facade. The client wants to fulfill an order, or wants to talk to billing, or wants to talk to shipping. But essentially what you're going to do is you're going to filter that client and then distribute them to the proper service that they want to get. So in this facade, the customer service class allows the customer to indirectly communicate and make requests to these other components through this facade. So what we're going to do is we're going to create classes of engine and headlights are going to be facade subsystems. So facade subsystems means that they're going to be these guys. These are subsystems, okay? So engine, basically, the idea of engine is that what is engine going to do? It's going to have a method called start. Because you have an engine, you want to start the engine. And if you have headlights, you want to turn them on. I'm trying to simplify it. Maybe you want to turn them off too, I suppose, right? Maybe you want to stop the car. But I'm just giving you some ideas. So the headlights and the engines basically are going to have methods that make sense for the engine. And headlights is going to have a method that makes sense for the headlights. So now, you're going to have a car. And so the car class essentially is a facade that structures the engine and headlight classes as part of the car. The client simply turns the car on and the subsystems go on automatically. So the car adds being a front end to the stuff that's hidden underneath it. So the car has a private engine, has private headlights, and so therefore when you construct the car, you can turn the key on or turn ignition key on. And what's going to happen is that ignition turning this on basically will turn on these subsystems. Oops, sorry. So in our driver program here, we simply create a car, and we say turn the car ignition on, and what's going to happen is the lights go on, the engine goes on. So we're sort of abstracting what we're doing by having the facade deal directly with those components, whereas we deal with an abstract, which is really pretty much the way we drive a car. When we come into a car, if we're going to turn the car, or some of us push a button for a car to start, what's going to happen is some things are going to happen. Like in my car, for example, when I turn my car on, the lights go on automatically. I mean, I can override that, but generally the behavior is the lights turn on, the engine turns on. Okay? I don't actually go in there and do this like we did in the 1920s, right? Although you've probably seen the movies, it's very, very funny. They have to get the spark plugs going on and stuff like that. But now we have all kinds of electronic systems, but actually a lot more happens when I push the button. Not just the engine comes on and the lights come on. There's a lot of technology that goes on too. My radar systems go on, right? The heating and cooling system goes on. Lots of things are going on. So you're pushing a button, but really lots of things are going on. So many things are going on. If you had to do them manually, it would be much more complicated. So that little turn-on button, ignition, acts as a facade into all the different subsystems. Okay. intrusive. So that's a facade pattern. All right, we have a composite pattern. A composite pattern is basically a composite. A composition is when things are made out of different parts. So you have a component, and then you have a composite. So notice that we have a certain UML relationship here. So client is depending upon the component. Okay? We may have a leaf, and notice that there's a dotting in here. Anybody know what the dotting means specifically in UML?
One reaction.
Somebody said it. Okay, so typically, so that means that this class implements or realizes this interface. So an interface is always an abstraction. So when you have an interface, it's abstract. Now in some languages like C# and Java, we have interfaces. An interface means it's abstract. You can never instantiate an interface. In C++, we don't have interfaces, but we do have classes that can be made abstract, which means you can instantiate them. So therefore, if it says interface, if you have this interface, this is a UML, what we call a stereotype. Stereotype. And what is a stereotype? Stereotype is like a technical comment. So when you see component, you say, okay, it's a component class. But when you see interface stereotype, it means that this component is an abstraction. Boom. Because it's interface. We could have used that in other places too, right? We could have used it in other places. If we go back to here, into our adapter pattern, we could have also used that. So in this case, we could have said that the target is an interface. We could have put a stereotype in here also. Okay, but we didn't. The adapter is a class that is subclassing this one. Okay, so going forward, so we have here, this is realizing this interface, and then here we have a composite. Notice that we not only have arrows of dependency here, so this is arrows of dependency, but also this is an arrow which is showing a composition. So there is a composite is depending upon 0 or more components. So that means we're making a composite. Okay, so let's take a look how this might work. So below we're going to create a composite design pattern for drawing objects. The common interface is drawing element, abstract class. And the two implementing classes are primitive element and composite element. So our drawing element class is clearly, it is a pure virtual class, so that's going to be our abstraction. And what is part of this drawing element class? We have drawing element constructor, which is real. And then we want to add a drawing element, and that's pure virtual. And we want to remove a drawing element, that's pure virtual. And we want to display a drawing element, also pure virtual. And then we have a virtual destructor, which we talked about last time. A virtual destructor is a destructor so that if you subclass a concrete class out of this one and you give it a destructor, the destructor will be called. If you don't have a virtual destructor, then the subclass is not, if you have a destructor, the destructor will not be called. So you have to make a virtual destructor if you're going to have subclasses that are going to realize this particular interface. So drawing element is kind of like an interface, although it does have some real stuff in it. It does have, for example, it does have a property here, and the property is called name, which can be constructed using the constructor here, but that constructor will be called by the subclasses, not by clients. Clients cannot call the constructor here because it's not a concrete class. So the clients can only call the constructor of the subclass. So we'll have to look at the subclasses of drawing element. And notice that we also are making the constructor what? Private. Do we need to have this constructor be private? Well, what does it mean when the constructor is private? It cannot be instantiated from any client, but it can be called from a subclass. Okay, so this is an abstract class with a private constructor. Okay, so now we're going to have a primitive element, all right? So it's the primitive element leaf class, so that's what we're going to have. We're going to have one of these things that's going to realize this one. So this is the component, this is our drawing element, this is going to be a primitive drawing element. We're going to have a primitive drawing element and a composite element. So the primitive element is a subclass of the abstract one that we had. And then we're going to basically have a primitive element constructor, the string name, which will then invoke the drawing element, which is this one, superclass constructor, because this is like the only real thing that we have, this one, as well as the constructor and the property. So we can actually store the property to this abstract class because it is actually implemented here. It's just the other stuff is not. Okay, so now we're going to have add, and the add method is an override, the remove is an override, the display is an override, and then we have a virtual destructor in order to destruct our concrete class. And then we have a private primitive element constructor, which is also made private. Why? So clients are not going to be able to construct it. Only subclasses can. Only subclasses. Okay, so the add element basically, we're going to have a drawing element, and we're going to have some real methods here. Now we're going to have a composite element. The composite element also is a subclass of drawing element. Okay, but in this one, our constructor becomes public. We also call the subclass constructor, and then when we want to add a drawing element, what we're going to do is we're going to go to an element and we're going to push back the element. What does pushback do? You remember? Where's that from? Ronaldo? Yes, so it's going to be from STL. So it's going to be an STL container. Okay, which I'm not really talking about it, but we have over here, you can see that we're going to have here vector drawing element pointer. So our where's it? Our property going to be someplace here? I don't even see it. It's going to be, is it in here? Someplace I need to have that vector. Right. Well, here it is. So on remove, I have it. On remove, but I don't have it as a property. Do I? Okay. Here we go. Okay, so it's on the second page. So here I have a vector, which is a drawing element pointer. So basically, the vector will contain drawing element pointers. Okay, and so the composite element will be a vector of drawing elements, which could be any concrete class of drawing element class. Okay, so you can see to add, we're going to go to our element vector, and we're going to push into it a value which is a drawing element. To remove, we're going to get an iterator into the drawing element vector. We're going to start the iterator at the begin pointer, while the iterator is not equal to the end. If the if the dereference iterator is equal to the element we're trying to remove, then we will erase it. And erase is a remove method on the STL vector. So we're going to remove this iterator, and then we're going to break. And if we don't break, we're just going to continue iterating through. So we'll only erase the elements or remove the element if we match it. Okay. So now in the display method, same idea. The display method basically is going to create a vector drawing element iterator, go to the beginning. While the iterator is not at the end, we're going to display this element, Okay, so we're going to basically, and this is just going to show you indentation plus 2, and you'll see exactly how, I think I have an output of this one. And then in the virtual destructor, while the element is not equal to empty, we're going to erase every element that we have. Okay, so here is an example of this composite pattern. So we're going to have composite element pointer root equals new composite element. We're going to call it picture. And then we're going to go to this composite element. We're going to add a new primitive element called red line and another primitive element blue circle and green box. And then we're going to create branches, or we're going to build this thing, so we're going to now add them. So we're going to say composite element comp equals new composite element, 2 circles, and then we're going to add to it the new primitive element, which is should be black circle, and a new primitive element, which is going to be a white circle, and then we're going to root add the composite to the root. So we're going to build our composite. So we have a relationship of one to many. So this is going to be made up of multiple elements. And then we're going to add and remove our primitive elements. So we're going to create this. We're going to create some of these. We're just using names for them. So we're going to create a new primitive element yellow line. We're going to add it. We're going to create a new primitive element orange triangle. We're going to add it. We're going to remove the yellow line. And then finally we're going to display. And as we display it, okay, I guess I don't have the output for it, but what's going to happen is we're going to basically, all of this is you're going to see the nesting of these elements. So that's how this composite pattern is going to work. All right. Proxy pattern, we already looked at a proxy pattern, but basically there are different ways to implement proxy patterns, and so we have different proxies. One of them is called a smart references, what we did with our smart pointer. We have protection proxies, we have remote proxies, and we have virtual proxies. So we'll talk a little bit about each of these proxies. So a smart proxy essentially is an outer object that controls access to the real object, which is on the inside. So the outer object is a reference or a pointer to the inner objects. The inner object is the real object, and the outer object is the proxy. So that's called a smart reference, is the proxy. So the outer reference is a proxy access to the actual inner element. Protection methods are proxy controls access to the real object or real subject methods by giving access to some objects while denying objects to others. So again, this is similar. The smart and the protection are different, except the protection is specifically guarding against illegal access. Remote proxies is a way to access objects that are not on the current machine, or possibly not even in a current computer system at all, but they are remotely located. And so a remote proxy gives you access to a pointer, which may then contact the object through what we call a skeleton, stub and skeleton. Anybody heard of stubs and skeletons? Ever heard of those things? Anybody? No? Well, basically a stub is a reference on the local machine that allows you to access an object on a remote machine. And sometimes we call the remote interface. So there's a local interface called a stub and a remote interface called a skeleton, and those stubs and skeleton actually implement socket connections that do the communication. So the client has access to the stub. It tells the stub to do something. The stub then makes a call, which is called a marshalling call, to a remote object, or a remote server, if you will, passing in the call to the method and the parameters. Then the remote object executes that command. It returns a value. The returned value is then sent back to the stub through what we call unmarshalling, and then the stub returns it to the client, and the client basically is like, oh, okay. So the client is not aware of the fact that the object is actually remotely executing. So these are example of this would be something like there's an old technology called Corba technology. Anybody heard of Corba? Long time ago. A Java implementation would be Java RMI, or Remote Procedure Call, RPC. Anybody heard of the remote procedure call? Probably, right? Remote procedure, nobody? RPC? Remote procedure call. But, so the idea is that a local client has a stub, it calls the stub to execute a method, the method executes, client's happy. But the stub actually does remote forwarding, or marshalling and unmarshalling. And there's actually typically two machines involved, although it's possible to have, so typically what you'll have is you'll have like a server, a proxy server, which is handling the remote methods. So essentially the stub contacts the proxy server invokes the method, the proxy server then unmarshals it back to the stub, and the stub delivers it to the client. That's what it is. So that's called a remote proxy. Virtual proxies, so probably more information than you wanted to know, but it is a proxy. Virtual proxies are essentially proxies. So let's say you want to have an object of type X, okay? And so you create object of type X, but you don't really actually create the object of type X. X is actually a proxy. So what you have is you're saying, okay, I want to create an object of type X, and the proxy says, okay, I'll make you think you have an object, but it doesn't actually create the object. And so your program is running, and then all of a sudden you have the need of actual method from the object. So you invoke the method. So the proxy says, oh, okay, I guess now you really do need the object. So then it constructs it on demand and has the object actually execute the operation for you, and you have it. Or perhaps it only has one object, and so let's say it doesn't create it for you, but somebody else wants an object, so it doesn't create it for that person. And then let's say the other person has a need of a method, so then it creates it, executes it, returns the value. And then when you need it, it's already been created, so it just executes the value. So the proxy might actually be sharing one object amongst multiple clients, or it may actually be waiting for late construction of the object until you need it. What happens if you never need the object? So the proxy never constructs it. So that's called a virtual proxy. Delay the creation and initialization of expensive objects until needed, where the objects are created on demand. Okay, so creating a real subject, we call the subject is the proxy, the hidden object inside, only when the do something method is invoked. Okay, so we have virtual proxies that create on demand when really necessary, not when you want it, but when it's necessary. Remote proxies that execute remote objects for you, and you think they're local. Protection proxies basically protect from dangerous operations or illegal operations, and smart references are essentially hiding the real subject inside, and we've done those. Okay, so what we have is we have the subject. The subject is the interface, that's the abstraction. The real subject is the implementation of the subject interface, okay, which represents the services. The interface must be implemented by the proxy as well, so that the proxy can be used in any location where the real subject is used. So the proxy has the connection to the real subject, and the real subject implements the subject interface. Okay, so let's see. I think we're going to look at, I forget which one we're going to do here. So we're going to do, so let's look at this example. I think this is very similar to what we did with a smart pointer. So what we're going to have is we're going to have a subject. So subject is going to be virtual. So that's going to be our abstraction is a subject. And notice the subject has a method called execute, which does nothing. It's a pure virtual method. So now, in order to make this reality, we have to then subclass subject and override our execute method. And notice that what happens. So when somebody wants to create a subject, they're going to need to create one of these things here. So and notice that the real subject is going to contain a string property. It's going to have a constructor which will take a string, which will store it into the property, and the execution will simply output the string. So that's what the real subject is doing. The real subject is actually just a class of a string that has an execute method that actually does something. So now let's take a look at this complicated, weird example, but it's not too hard, but it's kind of weird looking. Okay, so the class proxy subject, public subject. So you can see that proxy subject is going to subclass subject. So proxy subject is a subclass of subject, so that means it's going to have the execute method. So notice this proxy subject class will have a string. In fact, it will have 1, 2, 3 strings. So the proxy subject will have 3 strings, and then it will have a pointer to the real subject. Okay? And here is, so these are private properties. So these first, second, and third strings are private. The real subject pointer is private, and here is the public constructor. So the public constructor basically takes a string to the proxy subject, and it says int num is equal to s. What's s? S is a string. We're going to use a string class method called find first of space. So what we're going to do is basically in this code we're going to substring the different parts of a string. So I don't care if you specifically know what's going to happen. You're going to see the output in a second. And then we have a destructor. The destructor simply deletes the pointer to the real subject. And then we're going to overload the operator, and that's what kind of makes it a smart pointer. So the real subject pointer is returned by the operator, which is the parenthesis operator. It's the pointer operator. So the pointer operator returns the real subject pointer. So it's going to say cout first, space, cout second, space, and then return the pointer. And then the execute method, which we're implementing from this abstraction, is just going to output the first, space, the third, so first and space, and then the pointer will call the execute method. So if we construct this code to test the proxy pattern, we're going to say proxy subject object obj. We're going to create a string. So this is a string constructor. The quick brown fox jumped over the dog. That's a very famous English sentence. For some reason, it's used for typing purposes. If they want to test if you know how to type, they'll ask you to type this. So you might want to practice that if somebody wants to test your typing skills. I'm not sure how much that's done anymore, but certainly it was a classic. And so what we're going to have is we're going to say obj pointer execute. So as far as we're concerned, when we're saying obj pointer execute, we're executing the execute method from here. Well, what are we actually executing? Proxy subject execute method is here, right? This is the method. So it's going to output the first, space, and the third, and then it's going to output what? Space, and then it's going to say pointer execute. Well, what's pointer? Pointer is the real subject pointer. What's the real subject? See over here? So pointer equals to new real subject into s, where s is the string. So therefore, what's going to happen is it's going to say ptr pointer execute. So the real subject is going to point the execute method, and that's going to be the real subject. The execute method will output the entire string. And so what we get here, we get the brown fox jumped over the dog. Okay? And here, on the next one, we say obj pointer execute. So it looks to us like we're doing sort of the same thing, but we're not doing the same thing because obj pointer is an overridden smart pointer. And what's obj pointer return? Obj pointer returns first and second, and then it returns the pointer. And the pointer is the real subject. So it gives you a different behavior using the proxy. So this is really just a smart pointer version. All right. The next pattern we're going to look at, let's see what we want to do. There's bridge pattern. Let's see what we want to do. Bridge. I guess bridge, we'll cover the bridge. Will be our last structural pattern. Okay. So the bridge pattern is a structural pattern. So we want to separate the abstraction and its implementation and develop a separate inheritance structures. So we're going to decouple an abstraction from its implementation so that two can vary independently. We'll publish an interface in an inheritance hierarchy and bury the implementation in its own inheritance hierarchy. So it's beyond encapsulation. We're moving towards something called insulation. So let's take a look at how that's going to work. So let's look at the domain of thread scheduling. So we have a thread scheduler, And we're going to, a thread scheduler, when you schedule a thread, you have a bunch of threads that want to run in a single program. So the threads are all trying to run concurrently. Some of them are trying to run simultaneously. If you have one CPU, you can only run one at a time. So the scheduler has to decide which one is going. If you have 2 cores, then you could run 2 threads at a time. But what if you have 6 threads? If you have 6 threads, again, you're going to have either a time slice thread scheduler, which says, okay, you run for a little bit of time, now the next thread goes in for a little bit of time, now the next thread. If you have 2 CPUs, the thread scheduler may say, okay, these 2 threads can go in, and after a certain amount of time, I'm going to put the next 2 threads in, and the ones that were running before, they go back into the thread scheduler queue, and they wait for their turn again, and they try to basically time cycle all the threads. So all the threads are getting a little bit of time on the CPU, they wait, and the next ones get, and they wait, and so eventually everybody finishes nicely. So that's called a time sliced scheduler. Another one is called a preemptive thread scheduler, and a preemptive thread scheduler is a kind of scheduler that says, okay, now we have a priority of scheduling, so certain threads have a higher priority than other threads. So if you have a single CPU and you have 6 threads waiting in the queue, and the 7th thread with a higher priority comes in than all of them, he bumps the one in the CPU, it goes into the waiting queue, and the high important thread goes into the CPU and runs as long as it wants to. And when it finishes, it gets out, and then the preemptive scheduler can then put the next one in line that has the highest priority. So preemptive thread scheduler deals with priorities, bumping threads that have lower priorities in favor of threads that have higher priorities, and the time slice scheduler works only on time, giving each thread an equitable amount of time, same as everybody else. So let's say we have a thread scheduler class, and then we subclass as a preemptive scheduler and a time slice scheduler. But what we have to do is we are looking at 2 different operating systems. Let's say we're looking at Unix. So we have a Unix preemptive thread scheduler, and then we have a Windows preemptive thread scheduler. Okay, so we have 2 different kinds. And then on the time slice scheduler, we have a Unix time slice thread scheduler and a Windows. So we have 2 of those. So for each implementation of the thread scheduler, we have 2 operating systems that we have to implement it on. So let's say as we add a new platform, so again, Windows is a platform, Unix is a platform, we're going to add a new platform. And we're going to add a JVM platform, which is Java Virtual Machine Platform. So now, if we have a preemptive thread scheduler, we have to add now an implementation for JVM on PTS and JVM time sliced. So we're doing that. So as we add a new platform, our inheritance hierarchy is growing quickly, and as we add new thread scheduler, so now imagine that we have another thread scheduler. So instead of preemptive thread time slice, we have some kind of exponential thread scheduler. It's got a different scheduling idea altogether. So in that case, we would have to add this class, subclassing this abstraction, and then add 3 more implementations. So the problem, it works, we can do it, but if that happens, then we have to add a whole bunch of classes. So to add a new thread scheduler implementation, we now have to add 3 more sub-implementations. And if we add another one, it's going to be 3 more. And if we add another platform, then we would have to add our platform implementations for this one, and this one. So our inheritance hierarchy is scaling out of control a little bit. So imagine that we have 4 type schedulers. So instead of 2, we have 4 and 5 platforms. So if we have 4 schedulers and 5 platforms, that would require us to have 20 subclasses. And if we add another platform, we have to add another 5. So in this kind, so that's a design pattern. It's like, okay, each of them is going to require multiple implementations. If you add a new platform, you got to go boom, 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 boom on all the implementations. If you add a new scheduler type, you got to add all the platforms. So you can see that it could be a problem. So the bridge pattern proposes refactoring this sort of exponentially explosive inheritance hierarchy into 2 orthogonal hierarchies. So they're going to go in different directions. One is for platform-independent abstractions, and the other is for platform-dependent implementations. So the idea looks like this. So we now have a thread scheduler, and then we're going to, and this is an abstraction, it's going to be implemented by a preemptive thread scheduler and then implemented by a time-sliced scheduler. Okay? And now what we're going to do is we're going to have a thread scheduler implementation So the thread scheduler will depend on this, and it will depend on this, and it will be implemented here, and then we will implement the implementations only once on the platforms as they're being subclassed here. So let's take a look at how we could do a bridge pattern. It'll be a little bit more simple when you see it. Okay, so first we have a time-based interface. So notice that we have this. Is it a virtual class? Yes. Is it abstract class?
Yes.
It's not, because why? It's virtual, but it's not pure virtual, so it implements the method. Okay, so what we have is we have a class called time, and it's very straightforward. So basically, time has a default constructor. It also has a constructor for the hour and the minute. And in this case, it says, okay, IMP is a pointer to a time implementation. So this is time. Time implementation sounds like it's going to implement the time, which means it's probably going to extend the time class. So time-based interface includes a constructor for the hour and the minute. Okay, and then the constructor is going to call a new time implementation with hour and minute, because maybe we want to implement the time as a military time, or it could be GMT time, or it could be Eastern Standard Time, or it could be Central Time, could be Pacific Time, could be Mountain Time, could be China Time, okay, which I think they only have one time zone in China. Do you know that? One time zone in China. So when it's morning, one place in China, it's night in another place in China, but it's the same time. That's just the way they do it. Okay, keep it simple, right? They use the keep it simple philosophy. All right, but if you're in eastern part of China, then everything is pretty good, because most of the people were in eastern part of China, so that's fine. But the western part of China has a totally different behavior for their same time. At any rate, so our time constructor basically constructs a time implementation here, and then finally we have a virtual method called tell. And when you call tell on the time, instead of telling the time, it goes to the actual implementation to tell. Okay? So each time is going to have a pointer to a time implementation. So now we're going to have two different times. We're going to have civilian time. We could have civilian time, which could be just, let's say Eastern Standard Time. We could have military time. We could have Greenwich Mean Time. So clearly we can have different time implementations for the same specific time. So when you create a time object, I will create a specific time implementation. Okay? In the time implementation, you'll see what they're going to be in a second. So all we do here is civilian time is a subclass of time, which has its own civilian constructor, which is the hour, minutes, and then it decides whether it's PM or AM time, right? So the implementation here, notice this is our inherited member, right? Implementation is equal to new civilian time implementation, hour, minute, and PM. Okay? GMT is Greenwich Mean Time. So again, if we construct a GMT with an hour, minute, and zone, I'm going to create, because I have inherited from time, I'm going to create the implementation as a new GMT time using hour, minute, and zone. Okay, so now what we have a class called time implementation, and the time implementation basically will be a class which is going to have the hour and minute properties, and it will have a virtual tell method, okay, which is going to say time is equal to, and then it's going to give us the output that we want. But if we want the civilian time, it's going to give us the same thing, including AM and PM. So here's where we specialize it in this one. GMT, Greenwich Mean Time, time implementation will also be a subclass of time implementation. So we have a subclass of the implementation of time IMP, and time IMP, and these guys are subclass of the time abstraction. Okay, so finally you can see what the output is going to be. So the first thing I'm going to do is I'm going to create a time array of time pointers, because I'm not going to create any time. Well, I actually am going to create one of them. So I'm going to say time 0 is equal to new time 1628. Then I'm going to have time 1 is equal to new civilian time 428 1. So 1 could be AM or PM or something like that. And then time 2 is going to be new GMT time, 1628. Notice these are all going to be the same thing. And this is going to be a different zone for the GMT. And so as I iterate through this, notice that my time, the tell method is going to execute 1628 for the first case. For civilian time, it's going to say it's 4:28 p.m. And then finally for GMT time, it's going to say time is 1628 Central Standard Time, because I'm specifying the zone of the GMT. So now what I could do is I could create more, I can create another category. So I have GMT time implementation, I have civilian time implementation. I could ask you to implement, for example, in a project, let's say a military time implementation. And military simply means that it's going to be on a 24-hour clock. So, it's 11 o'clock, 12 o'clock, 13, 14, 15, like that, right? Also, that's military time. It's also the way they tell time in Europe. Usually people don't say AM, PM. They say, I'm going to meet you at 15 o'clock, and that means 3 p.m. Right? Anybody else use 24-hour clock in their country? You use 24-hour clock, right? When you're serving in the military. Anybody else use the 24-hour clock? 1,600 hours.
Workday.
Huh?
End of workday.
End of workday. Well, we have what? We have 1745. That's 5:45. All right, so that closes this one. Let me very briefly start what I'm going to do here. Obviously, I'm not going to be able to finish. And today I'm not going to keep you here for another half hour. But we'll just go to the last section very briefly, just so we can, we have a good jumping off point. Tell me when I'm at 3. Is this 3?
Yeah.
It is, very cool. Okay, so behavioral patterns, I think, are probably the most fun. Is that the one?
Yep.
Okay. Okay, so behavioral patterns are actions. So now we're talking about methods. And so, so we have something called the chain of responsibility pattern. Very nice little pattern. Did we talk about this one yet or no? For anything I know, in another class it came up because we're actually not implementing it, we're actually using it. Chain of responsibility. Which class do we have chain of responsibility? Huh?
Java, we use it.
In Java we did chain of responsibility. Yes, with filters. With filters, that's what it was. Okay. So some of these design patterns. So this is a very simple idea. I'll give you a very basic idea. So when we come back to it, you'll get the idea. So I basically create sort of a handler class, which is an abstraction, but it has a method, which is pure virtual typically. And then what I have is I have an implementation of this handler, and another implementation. And what I'm going to do is I'm going to have all of these handlers be like nodes, so they have pointers to each other. So I create one, then I create the other one, but I give it a pointer from the first to the second. And I create the third one, and I give it a pointer from the second to the third. And as I create the third, I may also give it a pointer back to the first. So it creates a chain. But each of these classes is not only chained like a linked list, but they're also having a method to handle something. So let's say a request comes into one. Okay? So a request comes into the first handler. If the first handler can't or doesn't want to handle it, it passes the request to the other one. And passing the request is defined in the superclass. So if you get a request, you can just say, okay, I'm going to chain it. And then chain it just goes to the next one. If this one wants to handle it, it can handle it, and the request is done. If it doesn't want to handle it, it can chain it to the next one. The next one, if it doesn't want to handle it, it chains it. It never, the actual handlers have no idea what they're chained to. They just pass it off. If they can't handle something, they pass it off. So if I don't want to handle it, I pass it off and might go back to the first one. Maybe the first one was too busy initially. Maybe it's not so busy anymore. Handles it. Thing is dead. Or done. Whatever. So it basically passes this chain of responsibility. So that's called peers. Those are all peers because they can all handle it. If they're not too busy, they can all handle it. Another one is called, we have an inheritance hierarchy. So basically, I only hire priorities 1 through 5. I hire priorities 6 through 10. I hire priorities higher than 10. So if somebody comes in with 8, this one says, I can't handle that. This one says, I got it. Okay, if you get 25, I can't handle it. I can't handle it. I got it. So that's called a chain of responsibility. They're passed until they're handled correctly. So chain of responsibility, that's one of them. So we'll come back, see how the implementation is done on that. Okay. I think I have, is that the only one I have? Maybe I have other ones. If not, then I'll add it in. Iterator, okay. You guys know what an iterator is, right? How many people use iterators in C#? How many people use iterators in Java? How many people use iterators in C++? Yes. Remember iterator? So iterator is a design pattern that's implemented in STL. Iterator is one of the design patterns. So iterator, we have observer. Observer is very nice. Observer is like this. So we're observing. So basically, I have a reference to an observer, and basically, I have a method that's going to make a beep sound. So basically, I'm saying, okay, I want you to observe when somebody comes into the class. So basically, the observer is just always doing something like this. So eventually, some event happens, the observer observes something, and the observer can then trigger a method in the client. So the client can do something, it can make a beep sound. Okay, somebody's coming in, so make an alarm using an observer. Okay, so that's another behavioral pattern of observation. So we'll cover that quickly next time. Observer pattern, we have the chain pattern. So chain, observer, iterator. I might throw an extra one in there next time. See you later. So